This conference will now be recorded.
Yes. Can you all hear me, guys? Okay, perfect. Okay, perfect. Thanks, guys. Okay, so I think we can get started. Okay. Uh, Let me first, kind of define the agenda, guys. So the agenda for today's and tomorrow's classes, we're going to be discussing big data. Okay, so when I mean by big data here, it doesn't mean that we're going to discuss the concepts which a data engineer should actually kind of understand. So it's not, basically big data related to a data engineer, but rather it is exactly how a data scientist or probably, a predictive modeler would need big data. So, at his perspective, at a data science perspective, or let's say at a predictive modeler's perspective or a data analyst perspective, how do you use all of these tools to probably make use of your analysis? I mean, how do you make use of these cases in your analysis? How do you play around with the data? So that's exactly what we're going to be discussing. Okay, so more about the admin part of it. So what happens if your cluster is like this? Or how do you configure your clusters like this? This is something that is really something that we don't have to be worried about. Okay, so it is taken care by separate set of people called big data admins. So let me first even give you this disclaimer before we start it. Our big data here, the discussions is going to be on how do you use all of these components, or how do you leverage all of these components for analytics purpose, or let's say for playing around with the data. So that is what we're going to be discussing. And also, let me tell you guys, I'm not a very great expert at it. I've used all of these components like 3-4 years back. Okay, it's been some long time on which I've worked on it. So I try to do my best, but if there's any questions, I'm going to simply say that I'll probably answer in the next class. I hope everybody is okay with that, right? So yeah, I think we can get started. So this session here, guys, the big data session, we're going to start off with introducing what do you mean by big data. Okay, so why do we need it? What else are the other ways of probably not using big data and still trying to solve all of these problems? And when it comes to big data here, let me first tell you, we are going to discuss about what is Hadoop as a basic, and we're going to tell how the memory management works at the back end. I'll try my best to do a good job there. Then we can speak about Hive. We can speak about HDFS. So how do you work with all this data? How do you use Hive to probably upload data, query it, do some joins. And then for tomorrow, we are going to be discussing about Scoop. So Scoop is more of a data ingestion tool. So how can you use Scoop to probably pull in some data, play with it. Then we'll also discuss Spark, more specifically, if I'm not wrong, PySpark. Okay, so we will try to use Spark and Python combination, and we'll try to understand how is Spark really helpful in munging a pretty big data sets here. So this is going to be our agenda. We'll first discuss what is big data, what are the different components that goes into it, and what are these individual components doing. And in our session, we're going to see a lot of examples on HDFS, Hive, Scoop, and Spark. Okay, it's going to be, in fact, a hands-on session. Okay, we're going to be doing it as well as discussing the theory part. It won't be pure theoretical. I'm also going to do a lot of examples. I'll be doing live coding, live examples right in front of your eyes. Okay, great. So let's first try to understand. So what exactly do we mean by big data? So what are the different things that goes into it? Why do we even need big data? So these are the first few questions that we're going to ask here. Okay. So I think I'll just kind of skip all these things. So let me come to this particular point. Okay. So the very first question that we need to ask is, why big data? What has this guy basically got to offer for us, right? What is the capabilities of big data? Why do you think that companies is probably widely accepting here this big data Hadoop platforms? Very simple, guys. So in our examples here, during our modeling sessions, luckily we have been playing with data which is not more than what, maximum 500 MB or a 1 GB of file, correct? So that is something that Python is able to handle because we have some good RAM in our systems, right? So we were able to work with what, probably a limited size of data, like maximum 500 MB file or a 1 GB or maximum even a 2 GB file, right? Provided you have some good RAM in your systems. But this is not usually the case. Typically what happens is you deal with loads and loads of data, right? So you have like what? You have loads and loads of data. So say for an example, if you're probably somebody who's working with a bank, you're going to see what data coming from several decades of cohort, right? Or probably if you're working with retail, you have a lot of customers of data, a lot of different products, a lot of different kinds of varieties of data that you'll have to probably work on, right? So there are in fact, there is something called as a 3V and a 4V concept in big data, isn't it? So you have something called as what, variety, velocity, right? Many other things, right? 3, 4 different V's and also. Basically, we are saying I have a lot of data with me. I want to basically start using all of this data in my predictive models. So when it comes to handling this particular data, guys, you need to make sure that you have the relevant software components with you, right? So that is when here in computer science, we have two types of computing we broadly do. The first one is something called a distributed computing, and the second one is something called parallel computing, right? So just give me a second, guys. Okay, so what we have is we have something called as a distributed computing, and then we have something called as parallel computing, right? So what exactly do we mean by a distributed computing? What do we mean by a parallel computing? So very simple, guys. In a distributed computing, right, what is going to happen is, as the name says, you're going to create probably a cluster of systems. Okay, you're basically going to go back and kind of connect multiple computing resources. Okay, so you're just going to go back and probably rent 10 to 20 different computers probably in a lab, and what you'll do is you'll just try to connect them in under a single network here. Okay, and then what you will start doing is you'll say, hey, me as the admin, no, I will start giving you the data as well as the code for the first system to work on. I will give the data and the code for the second system to work on. I will give the data and the code for the third system to work on. All the three people, the three systems that you're basically using here will carry out the job that you're asking them to do. They're going to come back with the results. Then you as an admin, you're going to aggregate the results coming from all the three systems that you've just connected here. So what happens? You just need some very simple commodity hardwares. You don't need to have pretty costly hardwares here. You're just going to take up very simple commodity hardwares, very plain systems. You're going to connect them under a particular network. And then, using some software components, say for an example, Hadoop, you're going to distribute the code and data to the different computing resources. They are going to compute and they're going to give you back the computed result, which you as an admin, you're going to aggregate all the results here. This is exactly what is called as a distributed computing. Why? Because you're distributing all of this code and data to several people so that several people can work in tandem, and you just have to take up the results from these guys and probably start aggregating it. That's it. So you don't need pretty costly hardwares, right? So because it's happening at what, at the same kind of a time, your time is also kind of getting saved here, correct? So you can't be doing it in a single system, wait as long as what, 2 years or 10 years for a job to get completed, but rather you can just put it through a lot of different commodity hardwares, get the results from them, and basically go back and aggregate it. That is exactly what is called as a distributed computing here in big data. So what do we then mean by a parallel computing? So when you talk about parallel computing, guys, this is a case where it's typically a single system, okay? it's usually a single system. Okay, so you can see here, a parallel computer is typically a single system where you will try to have multiple processors. Okay, so in the first case, it's what? There is probably one guy, he's an admin. He's going to share the resources, the data, the code, everything with all of these commodity systems. He's going to get the results and he's going to aggregate it, right? This is exactly what is called as distributed systems. One of your system could be sitting here in India, another one probably in US, another one probably in Canada, another one probably in Netherlands, right? You have different systems sitting in different parts of the world. You just pass on the data and the code to these people, right? And they're going to compute, you get the results. But a parallel system is typically one giant system. Okay, so typically this is called as MPP, massively parallel processing units. So you will have multiple processors inside a single system. So it's like you're trying to scale it up. This is like scaling up, while this is like scaling what? Horizontally. This is, you're trying to scale it vertically. Here you're trying to scale it horizontally. That is, you're trying to add a lot of systems here, while here you're saying, hey, in a single system, I'll make it more and more powerful, right? So the first case is a distributed system, while the second case is a parallel system where all of these guys are going to carry out their work in parallel. I mean, it's more or less same like a distributed system only, but the difference is here you can just work with very simple commodity hardwares, but here you require certain very, very expensive hardwares which can handle all of this data. Another difference is that here the systems can reside in different parts of the world, but while here it is only going to be a single system where there is only a single memory that is being shared by all of these different processors. Now suppose in case in a distributed system, one of the system is going down, the data is gone, it has got probably switched off. What might happen? There are other people who can carry out the same job for him, right? So let's say the fourth system is gone down. Suppose in case I've gone and shut down my system, I'm saying right now it's in maintenance, I'm shutdowning my system. So what happens? There are other three systems who can serve the job for us, isn't it? So these three people are going to still do the job of what a fourth person was actually doing. But here you don't get all those kinds of benefits, right? So once the system is down, that's it. All the processors are down, that's it. So suppose in case there's a natural calamity or something, if this system is gone, that's it. Your entire task is gone. You don't get any more systems to probably work on. But probably here it's not so. If one of the system is going to go down, there are several other computers which can still take up the job of what this guy was actually doing, which is exactly the benefits what distributed systems are going to bring for us. And the software that is going to sit on top of this guy, who is going to help us, handle all of these cases, is somebody called as Hadoop. Okay, named after a toy, basically an elephant toy. Okay, so the guy who developed this, right? He had a child. The child called the elephant doll as Hadoop. So he went on to go back and name this particular software component he was working as Hadoop. And in fact, every software component that you see here, right, is all going to be related to zoo-related items. Say, for an example, Hive. Hive is more like beehive, right? Then you have something called Zookeeper. Then you have something called Pig. Then you have something like, let's say, Scoop. So all the names that you're going to come across here is all going to be related somewhere around, the zoo kind of a scenario. Okay. So this is exactly what we have, guys. This is exactly the benefits that Hadoop, is actually going to bring for us. So we are saying that, hey, I'm not going to work on pretty small data anymore. I'm going to work on big data, which means I need the relevant big data systems which can handle all this big data. So we are saying, yes, you can do that provided you have two kinds of systems. One would be a distributed system. Number two could be a parallel system. In a distributed system, you are saying all the systems, are going to be independent. They can work, parallelly, and the results of it will get aggregated. So one of the guys is going to go down, another guy will take care of that same work. But in a parallel system, it's like a single guy. You're just scaling it up vertically, Anything that goes wrong there, that's it. The entire task is gone. So what makes our distributed system work like that is basically the Hadoop software distribution that we're going to take up, install, configure. He's going to take care of all of these things. He's going to make sure that there is a let's say a master and a slave kind of a tech at the back end, and he's going to make sure that all of these slaves are handled properly. And if there's anything going wrong with one of the slave systems, another person is going to probably work in place of that particular guy. So this is exactly what your Hadoop is actually bringing for us, guys. Okay. So Hadoop is basically more like a simple Java process. It's all basically processes at the backend. It's all basically Java-based softwares at the backend, which is going to help us enable all of this kind of distributed computing here instead of doing a parallel computing. Okay. So I think the next slides, everything is going to talk about the same thing. I don't really see a reason why we need to go back and discuss all these slides. So you can see this is about your parallel computing techniques, how you can do it. A cluster or grid, massively parallel processing, or high performance computing. So these are basically pretty costly hardwares which you may have to make use of to do your parallel compute. Or a much more easier thing would be what? To just go back and do your distributed computing using somebody called as Hadoop. Okay. So why Hadoop is exactly what we have discussed till now. So what do you think is the role of a Hadoop is exactly what we have discussed, right? So we're saying handle massive amounts of data, and also please make sure that you kind of handle them parallelly so that I can save a lot of time. And if there's going to be any loss in data, there's another person who can probably kind of compensate for it, right? See, guys. So what the slide says is, it's saying working with large volumes of data will require some very good analytical technology, right? Which obviously requires pretty good computational power. Hadoop here is basically a Java-based open source platform or an open source software distribution designed to work with huge volumes of structured and unstructured data. Okay. So you can do both the things. You can basically have structured and unstructured data. You just have to write codes which can handle your unstructured data here. Okay, so now you can see here, analysis of large such volumes of data has traditionally done through distributed computing here, right? So what is happening? Analysis of such large volumes of data has been traditionally happening through distributed systems. Now Hadoop is going to do the same thing, which will help us to go back and create and run all of these distributed systems in a much more better fashion. Okay, it can distribute your data more efficiently. It can automatically, run across all of these machines. He can pass on the jobs, he can pass on the data, everything, right? And then what are you doing? Within those systems, you're trying to do parallel computing here, right? So he says, I am a much more better framework who can do all of this distributed computing for you. I can just go back and pass the jobs to each and every person. I can monitor it, and I can also aggregate the data for you. So this is exactly what a Hadoop is basically got to offer for us. Okay. So what are the different features of Hadoop? So you can see here, Hadoop is capable of working on a large number of machines that do not share any memory or disk, which is basically going to do what? Help us solve, the problem of efficient storage and access. He's saying that I can just work across different very simple commodity hardwares where they're all going to be independent. So I don't have to be solving the problems of access related problems or not handling the storage properly. I don't have to solve all those problems. It's pretty simple for me because these guys are completely independent. And then he's saying the storage improves when data is loaded on a Hadoop platform because the Hadoop distributes the data over different servers. So he's saying I can improvise the data storage facilities. Why? Because I don't store the data only on one of the server. I keep copies of the data in other servers also. So I'm going to talk more about this feature in coming, slides, guys. But what this point is actually conveying is that compared to the conventional way of storing your data in a single memory, right? Hadoop is saying, I can distribute the data to the different servers, which means if anything is going to go wrong with one of the servers, suppose in case you are working on, let's say, a Mumbai server, it has got shut down. Don't worry, I've taken the relevant backup of all of this thing, probably in, let's say a Bangalore server. So I can just quickly switch on that particular server and I can start working on it, right? So he's saying, I can basically help you distribute this data over the different servers, and I can also efficiently track all the data stored on the different servers, right? And I can also run all this, task on these people in parallel over here, right? And then I can just go back and aggregate all the data here, right? So he's saying what? I can distribute the data. You can see by keeping multiple copies of data, which will help us basically have some robust systems against certain server failures. I can also track on what data have been saved where, what job has been sent to whom. I have some efficient methods of also tracking the same thing, running them in parallel over there, and also aggregating the results here. This is exactly what a Hadoop has basically got to offer for us. Okay. So just to kind of keep it simple, guys, what we have is Hadoop, who's going to push the data into different servers, keep copies of it, and you can work in parallel in all those systems, basically distributing the data. That's another beautiful concept here. And you're going to reduce time, not much of cost is involved, and it's an open source framework. This is basically what a Hadoop has got to offer for us, right? Now jumping into the different components of Hadoop, guys. So I think I'll open the next PPT. So when you talk about the different components within Hadoop, okay, so Hadoop is more like a software distribution, right? So if you ask the question on what are the different components that Hadoop has got to offer for us, the very first component and one of the most important component he has is something called HDFS. Okay, just give me a second, guys. Okay, so the very first component and one of the most important components that the Hadoop ecosystem has got to offer is something called HDFS. It's called Hadoop Distributed File System. So what do we have? We have the very first most important component of your Hadoop ecosystem. The first one, something called HDFS, which stands for Hadoop Distributed File System. That is number one. The second component is something called as MapReduce. Okay, I'll talk more about the MapReduce in some time. So the second most important component post HDFS is something called MapReduce. Basically, they are agents which can help you run programs. Okay, so to kind of keep it simple, map means he's going to give the let's say the work to different people. Okay, it's like you're giving it to different people, and reduce is more like take up the results and kind of aggregate it. That is exactly what is called as MapReduce. It's more about a methodology of writing programs. We don't use MapR anymore. Today's technologies, today Hadoop system, we don't use MapR anymore. In place of MapR, people have started using Spark. Okay, so we'll speak more about MapR and Spark tomorrow. You'll understand what is the difference between them. But the very first thing is something called Hadoop Distributed File System. Number two is MapR. Number three is something called YARN, Y-A-R-N. It's basically an acronym for something called Yet Another Resource Manager. Okay, so what do we have? We have YARN, which stands for Yet Another Resource Manager, which is component number three. Component number four is something called HBase. Component number five is Hive. Then you have Pig. Then you have Scoop. You have Zookeeper. You have Flume, and then you have something called Oozie. Okay. So in Hadoop ecosystem, guys, these are the different components that we're going to be using. Number one is something called HDFS. It's called Hadoop Distributed File System. So what is Hadoop Distributed File System? Now, suppose in case you have a computer which is probably having 100 GB of hard disk, okay? What you might probably do is you might allocate a small portion of it, okay, a small portion of it to this guy, somebody called HDFS. It's basically the same memory only, guys. It's the same hard disk only that you have, but a portion of it will be allocated to somebody called as HDFS. It's called Hadoop Distributed File System. Probably if there is 50 GB that you've allocated to him, this 50 GB will be local. It'll be called as a local hard disk, while this 50 GB will be called as HDFS. It's one portion of your hard disk which you're reserving specially for Hadoop. Nobody else can make use of it. It's specially available only for Hadoop. He is going to do his read and write operations on top of this particular guy. It's specially given for him. It's called HDFS, Hadoop Distributed File System. So we're going to talk more about this HDFS in some time. Okay, so I'll keep it aside, but just understand, guys. So Hadoop is saying, I'll take up different systems, I'll connect them under a particular network, I'll pass on the data and I'll store them into their systems, right? The question is, where would you store it? He says, I'm not going to store it in the local hard disk like what you have. I'll basically make a small partition, and inside that partition, I'll call it as HDFS. And in this HDFS file system is exactly where I'm going to store my data. HDFS, Hadoop Distributed File System. That's exactly where the Hadoop ecosystem is going to store or read data from. It's not going to read it from the local area, guys. You need to make sure that all the data that you're going to work on is available within HDFS. It's a partition of your local hard disk. Okay. So we'll talk more about it. I have a lot of points to discuss about HDFS. We'll discuss more about HDFS in a couple of minutes. The second thing is MapReduce, right? I'll talk about this guy in tomorrow's class, but as I told you all, we have something called MapR. It's basically like a programming methodology where they can distribute the work to different people, and they can also reduce the results back to form a single result. So that's called as MapR. We don't use MapR anymore because of a certain reason. We have started using something called Spark. So previously people used to write MapReduce programs in Java. Now people are not writing MapReduce programs anymore because you have a better technology today, something called Spark, which is capable of giving you programming capabilities using Java, Scala, Python, R programming also. So Spark is more and more famous today compared to the conventional MapReduce. In fact, MapReduce is like least used today. People don't use MapReduce anymore. That is component number 2. Component number 3 is called yet another resource manager. Okay, YARN basically stands for yet another resource manager. So what exactly do you mean by YARN? What is the job of YARN here? Once again, I'll keep it simple because we're going to talk in detail about it in some time. So YARN, as the name says, guys, it's a resource manager. Okay, so he is going to basically allocate the resources, the right amount of resources to the specific code that you've probably written. So say for an example, you're saying, hey, I want you to go back and create a linear regression model on this particular data. Okay. So what the YARN will do is, he is going to be the resource manager. He will say, hey, I think the guy has given me 1 GB of data, right? Let us split it into small pieces, this entire data. Let us push it to different systems. And I'll also make sure that I allocate that amount of resource for these systems. So I will say, hey, let all of this job probably make use of 1 GB of RAM. Okay, and I'll also probably use 3 servers right now. I'll span this particular process in 3 different servers right now. So he is more like the admin guy who's going to span your applications to the different servers that you've connected. Okay, so the multiple data accesses, or let's say the applications that is getting kind of spanned in the different servers, everything is being monitored, is being started by this particular guy, somebody called as Jan. He's called as yet another resource manager. So he will tell you, hey, which process has to be spawned in which system, and how much of RAM or let's say amount of hard disk is something that I have to give for him, or how many threads of process should he probably open there. All those things will be decided by somebody called as Jan here. In short, it's called Jan, but it's basically an acronym for something called as yet another resource manager. Okay. Now the fourth component, HBase. HBase is more of a database, guys. As the name says, HBase, right? It's more of a database. We call this as a columnar storage database. Okay, so it's going to basically do some searches in a column-wise fashion. That's why it's called as a columnar database. Okay, it's much more faster compared to the other conventional databases that we have till today, like say Oracle or other things. So it's a columnar database, and that's why it's called HBase. Because it's part of Hadoop, it's called HBase. Once again, a very famous database which is open source here in Hadoop, and people start leveraging it a lot. Okay, so HBase is more of a database, guys. So you can store all your data, proper structured data with the schema over here. So here is more of a file system. You're just storing the file as it is, but if you want to store it in proper databases and proper tables, etc., you need to make use of this guy, somebody called HBase. Okay, that is component number 4. Talking about the fifth component, we have something called Hive. Okay, so the fifth component is somebody called as Hive. So the Hive is a very important component, guys. I'll tell you why. Hive was basically developed by Facebook until they made it open source in the year of 2005 or something, if I'm not wrong. Okay, so Hive was actually designed by Facebook. So what these guys, the Facebook guys did was they said, hey, we have a lot of analysts, okay, in our system. I mean, in our company. These guys are capable of doing very good analysis, okay, but they're not very good software programmers. So they are not good people who know Java. They can't go back and write Java programs to do all of their analysis, okay, but they're very good analysts. They are people who can understand numbers, but they don't understand programming languages. So Facebook said, why don't we develop a particular product which is something so easy that you don't have to write a MapReduce program, but you can still write very simple SQL codes and allow your analysts to start working on big data stuff here. Okay, so Facebook came up with this idea. So they said, hey, we have a lot of people who are very good analysts, but these guys are not very good programmers. I can't expect them to go back and write MapReduce programs. So do you think we can just come up with a software product which will help our analysts to still make use of MapReduce, but in a very simpler fashion, and also handle big data stuffs? Now the answer was a beautiful product, something called Hive. So Hive is basically a SQL kind of a query engine. It's a query engine, guys. So you can store your data in HBase and you can query your HBase using Hive if you want, right? So what is Hive? A Hive is basically like a query engine. So you can write SQL codes to create databases, to create tables, to push records there, to write queries, to do joins, whatever you want, right? You can write SQL codes there. It's a beautiful query engine capable of handling big amounts of data, right? So HDFS is saying, I'll store the raw data as it is. Now using a Hive coding or something, you can try to parse all this raw data and you can probably save it into structured tables. You can save it in structured tables and you can start querying on top of this particular table. So this is exactly what a Hive is basically has got to offer for us. Okay, so the first one is HDFS, the second one is MapReduce, the third one is something called Yarn, the fourth one is HBase, the fifth one is Hive. Pig, right? What is pig? I can forgot what is pig. So let me come back in a minute, okay? So I'll tell you what is a pig in some time. Let's jump into Scoop, no? So Scoop here is more of a data ingestion tool. Okay, once again, a beautiful tool we're going to be discussing tomorrow. So Scoop is more like a single line of code that you write. Okay, so you're going to say, hey Scoop, I think it's a MySQL DB I have. The source is here. I want you to push my data somewhere else. Okay, so Scoop is more of a very simple tool, guys, which can help you with data ingestion processes. Okay, so this guy can basically write a single line of code and he can actually ask you to push data from one source to another area here. Okay, so this guy is somebody called a Scoop. It's basically a data ingestion tool. You just have to give your passwords, everything. You tell him that, hey, this is my database, this is a table I wanted to fetch and I wanted to push it somewhere else. So transferring data from one area to another, that's exactly what a Scoop can do for us. Right? So say for an example, you have an Excel file. Excel file needs to be pushed into, let's say, HDFS. You can write something. Then you're saying, hey, I think I have something in, MySQL. I want to read it and push it somewhere. He can do it for you. Hey, I have something sitting at Oracle databases. Read it and push it here. He can do all those things for us. So that is exactly what a Scoop is actually got to do, a data ingestion tool. Actually, Pig is more of a, it's a, I think it's a platform which can help you write MapReduce codes. So there is a coding language called Latin, if I'm not wrong, or this is called Pig Latin. I think this is completely called Pig Latin. So it's a person who will help you basically write MapReduce jobs actually. Okay, so that's what I think. So Pig is more of a programming framework, guys, if I'm not wrong. So you use this Pig to write a lot of MapReduce jobs. Okay, so you can basically write in this particular language. It's called Pig Latin, if I'm not wrong. And then you can push all your MapReduce jobs to the MapReduce that you see here, or even to the Spark if in case you want, and he can execute it for you. So I think it's more of a programming framework, if I'm not wrong. Pig Latin. Okay. So HDFS, a storage system. MapReduce is a person who's going to execute the jobs in a particular fashion. Yarn is going to handle the resources for you. HBase, it's a database for you. Hive, it's a query engine that is given. Pig is more of a programming framework where you deploy the jobs into MapReduce. The jobs that you write in Pig is deployed in MapReduce. Scoop is a data ingestion tool. You say this is the source, this is the destination. I want you to ingest the data from this source to this destination. The eighth product, Zookeeper. So Zookeeper is more of a monitor, actually speaking. Okay, so Zookeeper is more of a monitor. So he will tell you which program is running where. I think it's more like what a resource manager will actually do, but that's more relevant to resources. So resource perspective is what that guy will tell you. But Zookeeper will tell you about all the processes. He'll tell you, hey, is there a process working in MapReduce? Is there a process working in Hive? Is there a process working in Scoop? So this guy is going to be a monitor for literally all the processes you see here. He can monitor everything. So he will also make sure that it's available in the queue. Your processes are all available in the queue. He'll execute them properly for you. So Zookeeper is more of a monitor of all the processes, while this guy is a person who will monitor the resources. So he will say, I'll give you 1 GB of RAM for your work to happen. A Zookeeper will say, okay, I'm trying to monitor the process. Okay, if there is something going wrong, I'll let you know. If there's nothing going wrong, I'll still wait for the other processes to happen. So it's more of a monitoring tool, guys. He's going to monitor all the tasks for you. Okay, that's exactly somebody called as Zookeeper. Number 9 is Flume. Flume is more of a tool used for analyzing logs. Okay, it's basically called as a log aggregator. So today the world works with a lot of logs, right? So when you want to work with logs, Flume has been one of the most important tools people were using. But today you have people like NiFi and all who's actually doing the same task. And finally over to Oozie. Oozie is more of a automator, I would say, or you can call him as a scheduler. That's the right word. He's a scheduler. So you can schedule jobs here. So you can say, hey, right at 10 o'clock, I wanted to do something. I wanted to probably take a backup of my data, or I wanted to run this particular query. So Oozie is more of a scheduler, guys. So any task you write here based on certain rules and all, right? So he can work in a pretty automated fashion or in a scheduled fashion. He's going to run the processes that you're telling him to run based on the schedule that you give to Oozie here. So HDFS, MapReduce, Yarn, HBase, Hive, Pig, Scoop, Zookeeper, Flume, and Oozie. In our case, we'll be discussing HDFS pretty much in detail. We'll also understand Yarn, we'll understand Hive, and we'll understand Scoop. Okay, so these are some of the most important components. So where do you store the data? You know, how can you process it using Spark? How can you query it using Hive? How can you ingest data coming from different areas using Scoop? So these are some of the most important components that you need to understand. And in a given time, these are the different software components that we'll also be discussing in our course here. Okay. So what is HDFS? What is Yarn? What's Hive? What's Scoop? What do they do? How do you write the codes? That's exactly what we're going to be discussing here. Okay. A quick recap. Hadoop is basically what? It's a software ecosystem which can help you run the processes in a distributed fashion, right? It can also make multiple copies of the data and make sure of data resiliency, right? It's also a very good resiliency program you can see here. Since the task is working in parallel, the amount of computing time has gone down tremendously. At the same time, the cost involved in connecting all of these people using a beautiful Hadoop ecosystem is not much. One is Hadoop is open source, and this guy can work on very simple commodity hardware. Okay, and these are the different components that's going inside Hadoop ecosystem. So when you mean by Hadoop ecosystem, these are all separate software components. You need to go back and install each and every component here. So you need to download and install HDFS, download and install MapReduce, download and install Yarn. So all of these people are separate software components which you should go back and try to download and install it here. Okay. So any questions still here, guys? Were you all able to follow the different components? What are they actually doing? The names and the different areas where these guys will be used. Any questions on this one? Yeah. Okay, perfect. Okay. So let's talk about this slide. A small point that I could add on this slide. So in the previous case, while we were discussing, I told you all that you need to go back and install each and every component, right? It's like you'll borrow a Linux system, then you'll go back and download HDFS and install. MapReduce, download and install. Yarn also you'll download and install. HBase you'll do it. So on a Linux system, you're going to go back and configure all this, right? Doesn't mean it doesn't work on Windows and all, guys. It does work, but best suitable if you could use a Linux system. Okay. So this is one methodology of doing it, where you take a fresh system and you go back and install each and every component. Or number two is just like what we had in Anaconda, guys. So what is an Anaconda distribution? So we are saying I could have taken a fresh system. I could have installed Python myself. I could have downloaded each and every libraries. I could have downloaded the different IDEs I want, and I could have taken up all the pains of installing this, isn't it? But what did Anaconda distribution say? He said, just download my distribution. With a click of a button, you'll get all these components. All the components are a tick. In the same fashion, guys, now what we have is, we have beautiful distributions. There are already people who have worked on these systems. Okay, they have kind of connected everything together, and they offer in the form of what is called as distributions today. What are the different distributions available? You have a Cloudera distribution, something that we're going to be using today. I'll tell you how to make use of a Cloudera distribution. You can download and use the Hortonworks distribution. Intel, Greenplum, MapR, AWS, EMR. It's called Elastic Machine something, I think, EMR. Then you have your Apache distribution. So you can use any one of these distributions where all of these things are basically pre-installed. So you don't have to go back and take up the pains of taking a fresh system and installing each and everything. The distribution is going to come with all of these things pre-installed. You just have to open and run the distribution. All the components are available for you. You just have to start making use of these people here. So you have a Cloudera distribution, you have Hortonworks, you have Intel, you have Greenplum, you have MapReduce, AWS EMR, then you have Apache distribution. And in our case, we're going to be popularly using this one. I mean, we're going to be using a very popular one, something called Cloudera. Hortonworks and Cloudera is one of the most important things, guys. People use it pretty often. So they are open source to a certain extent, but when it comes to an enterprise level thing, they charge people for support. Okay, let's say you're working on a Hortonworks distribution, you have some problems, right? If you reach out to them, they'll basically charge you for support. So that is a business model that they have. They'll make sure that all of this is open source. They'll try to make you use it. But the moment you have some bottlenecks, these guys are going to come help you solve it, but it comes at a cost. So their business model is more of a support case. Okay. So in our example, guys, we are going to be making use of this Cloudera distribution. I'll quickly tell you how to go back and download all the Cloudera distribution. So I want you all to go to this particular link, which is cloudera.com/downloads quick VM, virtual images, okay, or virtual machines. So what these guys are giving you is they're giving you images, machine images already available. So you just have to go to this particular link. I'm going to drop the link for you all. You need to download the machine image for a particular platform. Okay, so I'll tell you what this platform is actually. I've installed a particular product called VMware. I'm pretty sure some of you will know what's a VMware, right? So whenever you have, let's say, a Windows system here, but you want to have a Linux system, right? You don't do a parallel boot, but rather you can just open a virtual machine here. So VM is called virtual machine. It's not your actual machine, but it's rather a virtual machine. In this system, there's another system that you can open. So based on whatever be the software product you're using, I'm actually using VMware. So choose VMware and you can just go back and fill the form and download all these things. Okay, it's going to download a zip file, which is typically 5.5 GB in size, if I'm not wrong. So it's a Linux system which comes with all the software products pre-installed. Okay. So you just have to hit this Cloudera distribution, guys. Go back and download the distribution, which is 5.5 GB in size. You have to download it, extract the zip file. The moment you have done it, you can, find the folder somewhere. So the folder will be something like this. You can see. So it will say Cloudera Quick Start VM. In my case, I'm using a version 5.5.0. So this is exactly how the folder is going to look like. It'll have the machine image here. Now what I want you all to do is, you need to open VMware. That's another product you should have installed already. Cloudera, you download it, okay? It's a zip file. And after extracting it, it's going to look like this, okay? I've extracted it and it looks like this. Next is you need VMware. Okay, so just remove it. Okay, next is you need VMware. You're going to say, hey, I want to open a particular virtual machine. Go to the area where you have extracted the download that you have just done. Go inside that. You can see he's saying VMware virtual machine configurations. Click that and then ask him to play it. That is, open this particular machine for us. So what did we do, guys? We went to the Cloudera distribution website. We have chosen VMware. We have downloaded it. We had a 5.5 GB file. We have extracted it also. Post extracting, you're downloading and installing VMware. Then you're opening VMware. You're creating a system by saying, hey, this is the VMware system. Now you're asking him to basically launch it. So the moment we click launch, you can see he's trying to launch this particular system for us here. It's a system within a system. It's a virtual image. So I want you all to notice a couple of messages that this guy might give you. Okay. So you can see that the system is getting launched. It'll give you a couple of messages. I want you all to just notice it. I'm going to talk about these images, the messages in some time. Let's see. So you can see it's a CentOS machine. So typically all this Hadoop is more suitable on a CentOS machine. Most of your prod systems, if you see, right, they will all be in CentOS, not in Ubuntu or anything else. CentOS is one of the most commonly used Linux type. So it's not giving any message. So then I'll switch off the system and I'll let you all know. Okay, so let this happen. Probably, once you're done with it, I can just switch off the systems and I can let you know. There's a small message I want to, kind of help you out all understand. But anyways, so let it keep launching. Okay. So we were talking about the distribution, right? Now you know that you don't have to take up the pains of taking up a Linux system and installing each and every component. Rather, you can just go back and download a particular distribution and launch it here. You may use VirtualBox, you may use VMware, anything, whatever you like. You just have to go back and launch your system here, and then he's going to launch. All the software products are going to be available at your disposal right now. Okay. So it's open source, guys, but the moment you ask for more support, etc., then they're going to charge you. So that's the business model that these guys are basically following. Okay. So now what we will do is we'll go back and talk about HDFS. So the first component that we're going to be discussing is something called HDFS. So you can see it's a Cloudera system. It has basically got launched. I can make it as full screen. You guys should be able to view it. Guys, are you having any issues viewing the Cloudera system on the inside? Is the GoToMeeting still working? All good? Okay, perfect. So now you can just go back and exit the full screen, and you can just minimize it and start working on your Windows system here. But now suppose in case you want to go back to your Linux system, click the virtual machine, make it as full screen, you can start working on top of it. Okay. So this is called as a virtual machine. So it's basically a machine within a machine. You're launching this machine here and you'll use it. If you want, you can close it. You can open multiple instances of the same thing. You can go back and start another system also if you want, right? So that's the beauty behind virtual images here. What we've just done is we have launched a Cloudera distribution which comes with all these kinds of components that we've just discussed pre-installed. You just have to start using it. You don't have to take up the pains of installing anything here. It's a good means of practicing. So now what we will do is, guys, we'll go back and talk about HDFS. Okay, so I'll take up this PPT. So HDFS is one of the most core and the most important members of this entire Hadoop ecosystem. Okay, what is HDFS? HDFS is basically a Java-based file system, guys. Point number one is HDFS is basically a Java-based file system which is capable of handling large clusters of commodity servers here. It can handle any number of clusters you want, large number of clusters over here. Many a times, so sometimes I've seen a couple of cases, I've read about it, where people have been able to create systems which is capable of handling even 200 PBs of data. It's called petabyte or something, right? So 200 PBs of data also, or you can in fact combine 4,500 servers under a single network. I mean, a single cluster. There are cases where people have done this. They've been able to connect around 4,500 servers, where these servers will kind of handle 200 PBs of data for us. That amount of scalability is what this guy has already given us. Petabytes, 200 petabytes of data is what this guy is able to handle for us. So this guy can basically hold billions and billions of data. The programs are so efficient that they can handle them beautifully here, right? And HDFS is one of the most important, thing here, because it's basically the, the quantity of that enterprise data that is going to handle so beautifully. It's called Hadoop distributed file system, right? It's a Java-based file system which is capable of handling all of this data beautifully. So we call HDFS as a scalable. Why? It's because you can handle any amount of data. It's called fault tolerant, which means if there's anything that's going wrong, right, I have certain mechanisms, control mechanisms, which can just help you out, right? It's called fault tolerant. It's a distributed storage system. It's a scalable, distributed, fault tolerant storage systems that we have, which is capable of having concurrent data accesses for different applications, right? So what is this one? This is basically what? A scalable, distributed, fault-tolerant file system, which is capable of giving concurrent data accesses to different applications, which is enabled only when you have YARN. YARN and HDFS are going to work pretty close to each other. Both HDFS plus YARN will help you achieve all of these things that you're talking about here. Okay. So let's just try to read out the points available in the PPT. So it's saying what? It's a data service that offers a unique set of capabilities when needed for handling data volumes and velocities, right? It allows users to write file only once at a time. That avoids any coherences issues that might result from replication of data. It includes a file system called HDFS, that is HDFS that we're talking about. It's a useful, tough, clustered approach of storing and managing data files. HDFS is not the final destination for files. Unlike other file systems that constantly need read and write of data, HDFS writes data only once but reads it many number of times. HDFS ensures that it can be read from any cached copy of all files replicated on different machines without the need to verify whether or not the contents have been modified. Okay, so I'll tell you more about these points once we jump into the yarn and how they're working out. So HDFS, a scalable, fault-tolerant data system, the distributed data file system. Let me also introduce the next guy, somebody called as Jan. Okay. So what is this guy, somebody called as Jan? Do we have Jan anywhere here? No. Okay. So let me also introduce to you guys somebody called as Jan. Okay. So Jan is basically something called yet another resource manager. Okay. So what is Jan? Jan is something called as yet another resource manager. So the HDFS plus Yarn together, they will help you kind of handle all of this data, all of this processes, and aggregate the results also in the best fashion here. Okay, HDFS plus Yarn. So whenever you talk about HDFS, there are two components that you need to first understand. The first one is something called a name node. The second one is something called as a data node. So what are the two things? Two things are, number one, it's name node. The second thing is what? It's basically what? Your data node. Okay. While when it comes to Yarn, right, where it's basically helpful in managing all of the distributed systems, he is going to contain two very important components. The first component is called a central resource manager, and the second one is called per node. Okay, it's called what? Per node manager itself. Okay, so let me repeat, guys. Whenever it comes to HDFS, the two components that you need to keep in mind is number one, a name node. Number two is a data node. Plus, when it comes to Yarn, where both the people, the HDFS and Yarn, they need to work together. In Yarn, the two concepts that you need to understand are, number one, a central resource manager, RM. Number two is per node manager. That is, there's only one resource manager, but there are several node managers here. Okay. Now coming to the point. What do you mean by the HDFS's name node and data node? Okay. The first question is, what exactly do we mean by the name node and the data node? Very simple, guys. What the name node and the data node are actually doing is they are using a master slave kind of architecture. So the HDFS has been designed in this kind of an architecture. It's called as a master slave kind of an architecture, where the master is somebody called as name node and the slaves are the data nodes. Okay, so the master is basically the name node and the slaves are basically your data nodes. So what will happen is you're going to take one of your servers and you'll create something called as a name node. Okay, what is the name node actually doing? The name node is storing the metadata about what is the data stored in the individual data nodes that you see here. Okay, so say for an example, guys, this is probably a rack that you have. Okay, let's say for an example, here at Bangalore, I am probably creating a rack. Inside this rack, I'm creating my first server. There is a second server. There is a third server. Okay, let's say I'm having one lab. Okay, in that lab, I have three systems. I'm connecting the three systems: server 1, server 2, server 3. Since they are in the same location, I call them as a rack. Okay, it's a single rack which is having three servers right now. What will happen is one of the server is going to act like the master right now. He is going to hold somebody called as a name node. What is a name node? A name node is basically called as a metadata server. He's a person who's going to hold all the metadata about what data has been saved in this individual data nodes. So you'll have one data node here in server 1, another data node in server 2, another data node in server 3. But this name node will know which portion of data has been saved where and how much of data is available there. So he is the master and the other people are the slave. That's exactly the reason why we call this HDFS as a master slave kind of a. So what are we doing? We are saying let there be a name node who's going to be what? Your manager over here who's going to take care of all the metadata about what is the data that you've saved here. While the data node will say, hey, this is the data that has been saved inside my individual servers here. So these are all separate physical machines. This is one physical machine, another physical machine, another physical machine. Even this can come out of a different physical machine. So name node is going to have the metadata, whereas the rest of the people are all going to have what? The actual data here. Okay. So please don't understand that it's a separate hardware, guys. It's just more of a simple process that's running. Okay. Name node is what? It's a process. It's a Java process who will know what data is saved where. And similarly, the data node is what? It's a process. So he saves this particular data in the HDFS. Okay, he is saving it. So they are more like data processes. Please don't understand that they are probably a hardware or something. Okay, the data node is still going to use the underlying OS only. The underlying file system only to save this particular data here. Okay. So it's only in the data node that all the IO operations will typically happen, guys. In data node, only the read-write operations, the input-output operations will happen. In name node, I don't think there is any data, IO operations that's happening there. Okay. So in name node, there is no sort of IO operations that's typically happening. I'm talking about data-related IO. That's not happening, but in the data node, those things are going to happen. Okay. So let's just read it out loud. So HDFS follows the master slave kind of an architecture, where this HDFS cluster includes a single name node, as I told you all, which is going to be the master server, multiple data nodes that run on the HDFS cluster into individual physical machines. In HDFS, a file is divided into what is called as a block. I'll tell you more about it. A file is typically divided into something called as a block. These blocks of data are saved in the data nodes. So he's saying, I'll split the data into several blocks, into several data nodes. The name node master server performs operations such as opening, renaming, and closing of files and directories, while the data node is going to basically take care of what? The computing things and storing them, reading, writing, all these operations here. So you can see one of the server, data node, he will basically make sure that all the data is passed here, and he'll make sure that the metadata is saved here, while these guys are going to basically do the computations for us. Okay. Now, talking more about this block, there's a keyword, there's a very important keyword, something called block here, isn't it? We see that he's saying that the files are getting divided into something called as blocks, right? Let me tell you all about something called as blocks. So what happens is, guys, suppose in case you have a file which is probably 400 MB in size. I'll assume that is probably 400 MB in size, okay? Or let's say 300 MB in size. I'll say 400 itself, sorry. So we'll keep it as 400 MB in size, okay? What will happen is your Hadoop will divide this data into what is called as blocks of data. It's going to divide it into small segments, small pieces. So say for an example, if I assume the block size is equal to 100, he's going to divide your data set into 4 pieces here, 1, 2, 3, 4, where each of these guys are basically 100 MB in size. But actually, guys, the conventional Hadoop, right, they are using 64 MB block size, while only Cloudera distribution is using 128 MB block size. So the block sizes are what? They are basically 64 and 128 respectively. So the conventional Hadoop, if you yourself will download and install, right, by default it's a 64 MB. That is the original configurations. But the Cloudera guys, in their distributions, they have changed it to 128 MB file here. That is, they're going to make sure that each and every file is 120 MB in size. If the last file doesn't have it, it's okay. They can be less than 128 also, but at least the first few initial files will all be 128 MB in size. But the original size, the default size is actually 64 MB here. What is deciding the size, 64 MB or 128 MB? Simple, guys. It's more of a trade-off, okay? So people have been debating on this one pretty much. So it's more of a plain debate. If you keep a 64 MB block, right, what will happen is your data set will give you more number of blocks. That is, the number of blocks are going to be pretty high. Since there are more number of blocks, right, one advantage is I can quickly work on this particular data. That's okay. But the disadvantage is I need lot of servers which can handle this individual blocks here. So say for an example, if I have 400 MB file, right? If I were to use a 64 MB thing, I would probably end up with 7 blocks right now. What would I do? I'll probably end up with 7 blocks. So more number of blocks, but lot of servers that I need so that I can send all the blocks to the individual servers, ask them to work on it and collect the data back. While on the other hand, if I have 128 MB, the number of blocks required is probably only 4 blocks. So bigger data sets, so more amount of time to probably work on, but lesser number of servers that I need to probably connect to the cluster here, right? So I don't get to monitor many number of servers here. I just need to monitor 4 servers, while in the previous case I have to monitor 7 servers. If there's anything going wrong in one of the server, it's a problem. But here it's what? Monitoring only 4 people. Since here the data set is small in size, quick operation. But here the data set is high, little bit more longer operation. So the block size is actually speaking more of a trade-off, guys. It's a trade-off between how many servers to use and how much of time computation. It's more like a balancing act that you need to do. That's why today by default it's actually 64 MB size, but only in Cloudera it's a 128 MB in size. So what is going to happen is, suppose in case I have a file which is probably 400 MB. If I configure at the backend to have a block size of 100 MB, right? So I have what? 400 MB of file. If I configure it to keep what? 100 MB, he will end up with 4 different blocks. So what is going to happen? He's going to end up with basically 4 different blocks right now. So what will happen is the name node is going to say, hey, the first block on data you are going to work, first server you will work. The second block of data, I will share it with you, the second server. The third block of data, I will share it with you, the third server. The fourth block of data, I will share it with you, the fourth server right now. So we are saying what? We are saying that, see here, I have 4 blocks of data here, 400 MB in size, right? I'll just share the 4 blocks of data with the 4 individual servers here. So the first guy will work on the first block, the second guy will work on the second block, the third guy will work on the third block, and the fourth guy will work on the fourth block. So HDFS, Hadoop Distributed File System, what is he doing? The moment you upload a data file coming from your local to HDFS, right? And the moment you spawn a process, he is going to split this data set into what? As many number of blocks depending upon the block size that you have specified, and he will pass on the individual blocks to the independent systems that you have here. This is exactly the work of your HDFS cluster here. The name node will know what data has gone where, and the data node will basically store this particular data in the underlying OS right now. Now this is exactly the area where the work of a HDFS system is going to come to stop. That's it. So the HDFS is saying, hey, my work was to basically, split it and give it to the different people, right? I have done it. So I have given it to the different physical machines, the block of data here. Everybody has got one piece of data. Now the work is basically, they have to start working on top of it. But to start working on top of it, you need resources, isn't it? You need somebody to come and tell you that, hey, this much of RAM is what is allocated for you. Hey, this much of thread is what allocated is for you. So somebody has to come and tell, right, that this is the amount of hardware I'm going to give for you. Now comes somebody called as Yarn. What is Yarn? Yarn is called as yet another resource manager. So this guy has two components. What are the two components did I tell you? One, center cluster resource manager. Number two is per node data manager, right? Or let's say node manager. People call it with different names. So the first guy is more of what? A resource manager, while the second guy is more of what? A node manager. Now what will happen is a resource manager application will be spawned here. So there will be a small process that will start. The resource manager, he will say, I will also spawn individual node managers inside each and every servers here. He's saying what? Hey, not just data node for all of you. Jan is saying, hey, node manager is also for all of you. And now the resource manager will say, hey, don't worry. To the first server, I will give you 2 GB of RAM. I will give you 2 GB of RAM. For this process, another 2 GB. And for this process, another 2 GB. So the resource manager will allocate the resources. He'll say, in that physical machine, 4 GB of RAM is available, but I will give you your process for one block, probably 2 GB of RAM so that you can start using it. What is a node manager going to do? The node manager will be monitoring him. So this guy will be monitoring him. Okay, the data has arrived. HDFS gave me the data. Resource manager gave me 2 GB of RAM, the computing power. Now it has started computing. It's doing some processes. The node manager will know. Suppose in case the processes has, taken a lot of RAM. Now he says, I need more amount of RAM, right? So there is in fact another guy, something called application manager here. Okay. So I don't want you all to confuse. That's why I'm saying, let's forget this one. But usually there is somebody called, in fact, an application manager. The application manager will tell the node manager saying, hey boss, insufficient hardware. The node manager will tell the resource manager saying, hey, insufficient hardware. Then he will give the permission to make use of more amount of hardware. Then this guy will go back and say, hey, you can start making use of more amount of hardware. Getting what I'm saying, guys? Let me start again. So we had one data set. The data set was divided into small blocks. So let me assume there is a fourth server here. So block 1 of data was given to him, block 2 was given to him, block 3 was given to him, and block 4 was given to him. The 4 blocks of data was given to each and every data node that you see here. And the name node will basically keep the metadata about what was saved where. That is the area where HDFS work will stop. Now, coupled with this guy, there's another guy, something called Yarn, yet another resource manager. He will now start a process called as RM, resource manager, a single resource manager. He will also spawn processes, which is node manager in server 1, node manager in server 2, node manager in server 3, as well as node manager in server 4. 4 different services will have 4 different node managers. Also, when certain applications are getting deployed, right, there is something called application manager which will also get created here. Okay, They monitor the application. They try to understand what's going wrong. Is it more of a code problem or is it more of a hardware problem? Application manager will understand all those things. He will basically monitor the applications. If there is a hardware problem, application manager will tell the node manager will tell the resource manager will give permissions to make use of more resources. Then this guy will go back and say, hey, make use of more amount of resources and start doing your computation here. So all of these things are very important, guys. Now you know, right? Why do you need a data node? Why do you need a name node? Why do you need a resource manager? Why do you need a what? Node manager. So these guys are basically what? They are processes which will store metadata here, and he will store data here. But the moment the job is coming, that is the code and the data is coming to this area, you need computation power. So the resource manager will say, you can make use of this much of computing power. So that will be monitored by somebody called application manager. When something goes wrong, he will tell node manager, he will tell resource manager, he will get a reply back, and he will pass on that particular reply here. So this is exactly what the HDFS and the yarn together are actually going to do for us. So the HDFS is going to make sure that the data is getting distributed, while the yarn is basically going to monitor all the processes and make sure that the resources are getting allocated here. So the first guy is worried more about the data, while the second guy is worried more about what the resources for this particular computations to happen. Okay. And in fact, another small work of your data node is, guys, typically the data node will use something called as a heartbeat signal. Okay, I think it happens for every 5 seconds or 10 seconds. I don't remember exactly. There's something called as a heartbeat signal. All the data nodes will pass on to the name node just to tell them that, hey, I'm still operating, that there is nothing really going wrong. Okay, so the data nodes will tell the name nodes with a heartbeat signal that, hey, I'm still running some processes. Okay, I've still been operating. The moment the heartbeat stops, it means he's not operating anymore, which means something has gone wrong here. Okay, so these are the two different things your HDFS and yarn is actually doing, guys. HDFS taking care of distributing the data, yarn is taking care of managing the resources for the computations to happen on top of this particular data here. Okay, any questions still here, guys? Did you all follow what is a HDFS doing and what is a yarn doing? What are the different components of your HDFS and what are the different components of your yarn? Did you all follow, guys? What is this data node? What is name node? What is resource manager? What is node manager? Clear till here? Yep. Okay. So let me just do something. I'll help you all understand this node managers and all. Actually speaking, guys, if you have taken up a Linux system, okay, and installed all the Hadoop, right? You need to open the terminal, okay, basically the command line here, and you can type something called JPS. So here in Cloudera, we have opened the system, we have the terminal. You have to type JPS, basically stands for Java processes. The moment you hit enter, he's going to tell you all the Java processes which is actually running at the backend. So which means if you have configured your your systems, everything on your own, right, you'll be able to see name node, data node, resource manager, everything here. I'm not very sure why it's not showing here. One reason is because it is getting started by default. Okay, so that's why they're not really showing it as a separate Java process here. So the reason why I wanted to help you all show the message, because it'll tell you that it's kicking off all of these processes here. So actually speaking, guys, if you're installing your own Linux system and Hadoop, right, the first thing we do is we say start all.sh. So there is basically a script here. We run this. It's called start all.sh. Initially, it used to be start dfs.sh, then another command yarn.sh. We used to run it 2 times. One is start dfs.sh, which will start all the Hadoop distributed file system related processes, which are name nodes and data nodes. While when you say start -yarn.sh, it'll start your resource manager and node manager, which was later combined into all, which will start all the processes for you. Here in Cloudera, we don't have any such sh file, okay, because it's starting by default. They are actually starting by default. So let me help you all try to understand that. What I will do is I'll shut down this machine. Okay, so while shut down, it should surely tell you. So shut down this one. Let's hit yes. You can see the machine messages here. He's shutting down something called Hue. Okay, can you see? Stopping the data node. He's stopping this process. Then something called journal node. We don't really need a journal node. Can you see? Name node. He's stopping this particular name node. Secondary name node. Basically, it's more like a backup. If anything goes wrong in that name node, secondary name nodes will start. Okay. So similarly, you should talk about resource manager, node manager. Can you see? Then it should be a resource manager. Can you see resource manager? He's stopping all of these processes right now. So actually what is happening is by default, all of these guys are, getting started. Can you see HBase? It has also got stopped. Right? Then Thrift, this is another one. Hive, can you see? Scoop, can you see Scoop server? All of these processes are actually starting by default. That's why when we go back and say JPS and hit enter, it's not listing it. But actually he should be doing it for us. Okay, so when you go back and ask for JPS, actually he should be telling us that these are the list of Java processes which is actually running. So it's only in this distribution that these guys have kind of stopped it. But if you build your own system from scratch, when you do JPS, you'll be able to see it. Okay, he'll tell you that these are the list of Java processes which is actually running at the back end. So please understand, guys, these guys are all basically processes. Okay, they are all Java codes which is actually running here. Okay. Okay. So before I move on, I just noticed a question. In case of single server, one name node and data node can be present. Exactly. So if you have a single server, it'll be one name node and one data node. Okay, so this is a system that we have, right? What we are launching right now is going to have only one single data node and one name node, obviously. Even if you have multiple servers, it's always going to be one name node only. So if suppose in case this server goes down, right, then there is something called as a secondary name node, which will start off in some other server. So this name node is saying, hey, I have the metadata about what block of data has gone where. What if in case this server current was actually pulled out? So this has stopped working. Then in a different server, there is something called a secondary name node, which will actually launch here. So there's a secondary name node which will launch here. That's another process. It's a backup of your primary name node. Now that guy will start handling the metadata process, what your original name node was actually doing. Okay. But if your question is, if it's a single server, yes, a single server can have one name node and one data node only. But if in case you have multiple servers, once again, one single name node only. But if there's anything that's going wrong here, then a secondary name node will be launched in a different server. Right? So if something happens to the data node, another person will kind of handle it. I'll tell you how he's handling it. So if a name node is going to go down, how is another person going to handle it? Because there's a secondary name node process which will start off here. Okay, so this is called name node, data node, and the yarn which is doing your resource manager and your node manager here. Okay. Okay. So now let me talk about another important thing, guys. The first thing is we understand HDFS is a distributed file system, right? Which means he's saying what? I can take up the data, split them, and distribute it to different people. Because I can distribute the data to the different people here, and the different people can start working on top of it, right? That's exactly what a HDFS is actually telling us. But the HDFS also told us that for resiliency purpose, that is for resiliency purpose, I'm going to keep copies of the data in the other servers. He's saying what? I'm going to keep copies of the data. That is, I'm going to replicate the same data in other servers also. So what happens is, guys, here we have a configuration, something called replication factor. By default, it is equal to 3. Okay, by default, it is equal to what? It is equal to 3. Suppose in case you have a data set which was divided into 4 pieces: block 1, block 2, block 3, and block 4. Okay, a 400 MB of file which was divided into 4 blocks, each 100 MB. Now you are saying replication factor is equal to 3. What your name node will do, guys, he will say the block 1 should be shared with this guy, block 2 with this guy, block 3 with this guy, and block 4 with another server. Correct? That's okay. That is what is called as distributed file system. You're distributing the data to different people so that they can work on it. But where is the replication happening? Where is the resiliency happening? Since you're keeping a replication factor which is equal to 3, what your name node will do is all the blocks here, right, they will get replicated. There will be duplicates that will be created, and the total number of times you will see this is equal to 3. That is, the same block will be available 3 times. 3 replicas will be seen. So what will happen is the first replica is over here already, we know. The second replica will be shared with another person. Okay, and the third replica will be shared with another server in the same rack. So I'll talk more about it by creating a quick diagram here. So see here, guys, let's say this is one rack of system you have, another rack of system, another rack. Okay, so when I mean by rack, let's say this is Bangalore, let's say this is probably Mumbai, let's probably assume this is Singapore. Okay, here there are 3 servers with me: server 1, physical machine 2, physical machine 3, physical machine 1, 2 and 3, 1, 2 and 3. Just assume you have 3 laboratory guys. So lab 1 has 3 machines, lab 2 has 3 machines, lab 3 has 3 machines. So this is called rack 1, this is called rack 2, this is called rack 3. So this is host 1, same host, the same host. So this is a Bangalore host, this is a Mumbai host, this is a Singapore host. Now somebody gave you a file. You divided it as, let's say, 3 pieces. Okay, block 1, block 2, and block 3. What will happen is block 1 will go to Bangalore, block 2 will go to Mumbai, block 3 will go to Singapore. So this server in Bangalore will work on it, this server in Mumbai will work on it, this single computer in Singapore will work on it. So this is distributed. The first property we understand, distributed, how they are getting distributed. Number 2 is replica. How is he making replicas here? When we keep a replication factor is equal to 3, the block is basically going to get replicated 2 more times. So total number of replicas is equal to 3. So what is going to happen is, guys, so I think I'm making a mistake. So when I mean by replica is equal to 3, I think 4 only. Yes, I'm making a mistake, guys. So there's going to be 4 blocks. So yeah, now I'm correct. So there'll be 4 blocks you create. Replica is equal to 3, which means 3 copies of it. So totally 4 blocks of the same data. So what will happen is the first block has already been shared with this guy, correct? First block was shared with Bangalore. The second block will be shared with Mumbai. What will happen? The second block will be shared with Mumbai. Now what will happen is the third block will be shared with Singapore. The fourth block will be shared with another server in the same Singapore area. Okay, so even if there's a fourth server, right, it will not go to the fourth server. This single block will not go to the fourth server. Okay, so what we are saying is, we are saying the first replica will be given to any random node, which is this guy here. The second replica is made sure that it is in a different rack altogether. And the third replica is made sure that it is in the same rack but in a different server here. Okay, what is the reason? The reason is simple. If this guy goes down, this copy of data 1 is available in the Mumbai server, isn't it? So data 1 was available here. Suddenly, let's say there was like massive downpour and this system has got shut down. Because there's a copy of this data, a server in Mumbai can start making use of this data and he can do the same job what Bangalore server was supposed to do. Right? This is the Mumbai server going to do. Suppose in case even the Mumbai server is going to come down, then you have the Singapore servers. Right? So you have 2 people here. So it is actually the same Singapore host, but there are 2 servers right now. So what is the reason for having, like, 2 servers here? It's basically like, see here, even after this is gone, I have the last choice here. I will just choose one of the guy who is most closest for me. That's it. That is the only reason. So one is Bangalore gone. Next was Mumbai. So if Mumbai is also gone, Singapore. But now already I've wasted a lot of time, right? So now I will ask, in Singapore, these 2 servers, who is most closest to? Who's going to take very less amount of time for me to kind of make the data access and make the data transfer? Now you'll say, hey, I think this server is much more faster because it has a higher bandwidth. So you can use this server in Singapore to do your computation and transfer the data that you want. So any more amount of replicas you do, say for example, when you do replication as 5, no? So the first guy will be here, second guy is here, third guy is here, then fourth will go here, fifth will go to a different server, that's all. But always the third replica is made sure that it is in the same rack, but on a different server where replica number 2 is available. Because original data is already gone, already late. The first replica is also gone, already late. So the third replica should be used, right? But the point is, should I use this guy or this guy? The yarn will decide who is most closest, who is having more hardware, who is having better bandwidth in internet. I'll make use of that guy to do my computation and transfer all my data here. So this is exactly what is the replication concept, and this is exactly what is going to keep your data resiliency, in place. The data resiliency is actually kind of maintained here. So if one of your server with all the data is going to go down, don't worry. The copy of that particular data is always made in another server. So you can make use of that data even if this server is going to go down. This is exactly what a yarn is going to do and a HDFS is going to do combined. The HDFS will know which data has gone where, and the yarn will know which data has to be accessed right now because it's already time. I need to access the guy who's most closest to. So the yarn will know which guy should be accessed right now so that we can immediately do the computation and kind of fetch all the outputs right now. This is also a very, very important concept of something called as replication factor here. So they don't just divide the data and share it across with other people. They also make replicas of the same data in other people. Why replicas? Because suppose in case something is going wrong in one of the server, the other servers can just go back and do the same job of what these servers were actually supposed to do here. So both these jobs combined, guys, is exactly what a HDFS and yarn is actually going to offer. Okay, so what is happening? HDFS is saying, I'll give you data nodes and I'll give you name nodes. And the yarn is basically saying, I'll give you resource manager and the node managers. Okay, so I can probably, help you all summarize this one finally. Okay, so say for an example, we have our entire system like this. Okay, HDFS system. Now let us assume there are individual servers. Server 1, there is server 2, there is server 3, and there is server 4. There are 4 different servers with us. Okay. Okay. Now what will happen is your HDFS will basically be here. The yarn component will basically be here. So what is HDFS saying? HDFS is saying, okay, in this physical machine, I will launch the name node process. And the yarn is saying, in this physical machine, I'll launch the resource manager process. Okay. Then the name node is saying, I will create one data node here. I will create another data node here. I will create another data node and finally another data node also. So here what the communication is like two-way, right? So the name node and the data nodes are going to get connected because heartbeat signal is always going to happen. The data node will always pass heartbeats to name node saying that I'm still alive, and name node is going to basically say this much of data for you. So what happens is you'll have HDFS client, okay? So they will share the data through name node to all of these people, okay? Then what you have is you have a yarn client. You call this yarn client. He's spawning a resource manager process here, and now the resource manager is saying, hey, I will launch a node manager here. I will launch a node manager for this guy, another node manager here, another node manager here also. So this guy is saying, I'll work on a block of data. He's also saying on a block of data. He says, I'll work on blocks of data. I'll work on blocks of data. Not a single block, okay? Many blocks also they can receive. And this guy is saying, okay, I'll give you the container where you can go back and execute all this. That is the RAM that you require, the number of threads you require, how parallel are you going to do. I can give you all the hardware over here. So this becomes your complete architecture. Here also the communication is two-way. Between resource manager and node manager, the communication is going to be two-way right now. This becomes your complete architecture of your HDFS and yarn together, guys. The two very, very important components, the backbone of your entire Hadoop distributed file system. Okay, right? So any questions till here, guys? Do you all agree till here? Do you all follow what is HDFS? What is yarn actually doing? Yes or no? Any questions till here, guys? Any questions on HDFS and yarn? Do you all follow the different components of HDFS, the different components of yarn? What are they launching? Why are they launching? Yep. So far, so good. Okay. Cool. Okay. So what we can do is, guys, let's probably take a quick break. We can probably take a 10-minute break, possibly. Okay, then let's be back. We can start doing a lot of HDFS codes right now. Okay, we'll start doing a lot of HDFS codes. I'll tell you, how to access your HDFS, how to push data, how to remove data, edit data, everything. Okay, so we're going to talk about HDFS next, all the different commands that you should know about HDFS. Okay, so this is going to be the point of discussion post the break. So let's be back probably in another 10 minutes. Okay, thank you guys.
This conference will now be recorded.
Yes, so are you all online? Okay, perfect. Okay, so I'm pretty sure you would have understood how to download this Cloudera distribution and launch it, right? So I gave you the link. You just have to go back and choose VMware and fill the form, let it to download. It's going to be 5.5 GB. Then you just have to extract it and keep it here. Install VMware and launch it using VMware. Okay. And the moment you launch it, this is exactly how it's going to look like, right? We have anyways, recorded all these things. You can just refer it. You can refer the recording on how to do this. So now what we can see is, guys, so this is exactly the UI that you have for the Cloudera system that we've just opened. So you can see generally like what every other system will have, it'll have all these applications here. So the terminal is one of the most important applications for us. So we are opening the terminal. So we're going to be doing everything in this terminal only, okay, including the Hive, scope, everything for tomorrow. Also, it's going to be on the terminal only. So since this is already installed with Hadoop, you can just simply access your HDFS using simple commands, guys. Basically, these are all very, very simple commands, okay? By probably the end of the class, I'll upload all the commands in the drive. But for just now, just understand how the commands are working. It's very simple, actually speaking. So you're going to start off by saying HDFS, DFS. This is always the command that you need to start off with, okay? HDFS, DFS, which means you're trying to do some kind of action on this HDFS that we've created. The action could have been, let's say, moving a file, copying a file, removing a file, understanding what is available on the inside, or how much of memory has been probably taken up. So anything that is something that you have to do it on the HDFS, please make sure that you use HDFS DFS at this very starting. Okay. So now see here, we're going to say HDFS DFS hyphen ls. Hyphen ls means what? Basically list what are the files available in this particular link or in this particular address. So I'll just give it as a slash. We'll find what is available in the root directory. I can probably call it as. Let's hit enter. So the moment you hit enter, he is saying, hey, within the HDFS, okay, we have benchmarks one folder, we have TMP one folder, user one folder, VAR one folder. In HBase, you have a folder, something called HBase itself. So he's saying, hey, these are the people, okay, it was created at this time. You have benchmark, you have HBase, you have temporary, you have user, you have VAR. So these are the different folders available is what he's saying. So the path, sorry, the command is what? HDFS DFS hyphen ls. Now what we will do is we'll go back and say, hey, I wanted to probably create a directory right now. So we will say HDFS DFS mkdir is called as make directory. So HDFS DFS hyphen make directory slash. What is the directory name that you want to create? I'll probably call it as data. I'll hit enter. The moment you hit enter, you can see. So it is in safe mode. Okay, so to remove it in safe mode, just give me a second, guys. I need to quickly Google it. Actually, sudo leave safe mode something, I guess. It's been quite some time. Okay, so just should do it. HDFS. Okay, yeah. So this is basically a safe mode, guys. These guys don't allow us to change anything here. So first you should make sure that you're exiting your safe mode. Okay, so please do make a note of it. So you're saying HDFS, DFS admin. So this is a safe mode. What is the command? You're asking him to leave it. Okay, so we are asking him to leave it. Now we'll go back and run our original command where we said HDFS DFS, make a directory inside this HDFS specifically. What is the directory? Data. Let's hit enter. The moment you've hit enter, you can see there is no messages, nothing. So he was probably able to create it. Now let's go back again and ask, hey, can you please list what is available in this particular root directory? He's saying, of course, yes. Along with benchmarks, temp, and user VAR, now you have the new folder that you've just created, something called data. So it's saying 29/06/2090 at 6:41, the folder was created. So you can see that we were able to create this particular folder by just saying mkdir, make directory. Okay. Anybody who's played with Linux, right, you'll feel it's very simple. You just have to add HDFS DFS at the very front. It's the plain old Linux commands, that's all. So similarly, in the same case, there is also LSR, okay? So LSR is like, recursively, please let me know what is available on the inside. So he'll go and search every folder. Within every folder, what are the files available? He'll kind of populate everything. It's called recursively. Can you see? He's going into each and every folder that you have, right? Every possible folder, every possible file is what he's going to launch for us. So you can say LSR or you can say LS and a separate argument -r, which means recursively. You're saying, can you please let me know recursively on what's happening? I think it's capital R. Okay. So recursively, please let me know what are the files available within each and every, subdirectory also is exactly what we're asking right now. So to clear the screen, plain old Control L only, like what you would have done in Spider and R. Okay, so we have spoken about -ls, we have spoken about -lsr, we have spoken about mkdir, right? Next is we'll talk about a function called put. Okay, let's talk about something called as put right now. So what I will do is, guys, I'll move one file inside this particular image. Okay, It's a very fresh image. So what we can probably do is, I'll move one CSV file right now. Just give me a second. I'll just quickly search for a CSV file. Okay, so see guys, so this is a file I have. I'll just drag it. I'll go to VMware. I can just release it. Okay, this is more than enough. You can easily transfer from your main system to your image just by dragging and releasing it here. So the moment you have done, you can see your insurance.csv file is available here. Okay, so you are able to move from your original Windows OS or something to this Cloudera OS. Now, where is this guy getting stored? He is getting stored in the local area. That's it. It's /home/Cloudera desktop. It's in the local hard disk. It's not in HDFS yet. It is inside the local hard disk right now. So you can go back and ask, hey, how about please letting me know what is available? You can see that file won't get populated because it's in the local disk. It's not in the HDFS disk. Now what we're going to do is, we're going to go to this particular guy. We'll ask him, what is the path? Where are you probably located right now in the local area? We'll copy it. We will say HDFS DFS. I want to put a particular file. The command is -put. I want to put a particular file coming from this particular source. The name is called insurance.csv. What is the destination? Where do you want to keep it? I'll say in the HDFS / there is a folder called data. Inside that particular folder is what I want you to save it. So we are saying HDFS DFS -put. The first one is something called local source. The second one is called destination. We are saying, hey, this is a source I want you to take from the local, push it into this HDFS destination. The moment you hit enter, you can see he's going to run some processes at the back end to move it from the local to your HDFS. Now go back and ask ls and go inside your data folder. You'll be able to see the insurance.csv. Can you see? He's saying the insurance.csv is available. It is created at what time? 6:45 just now, probably, right? You can see 2019-0629. So the system time is what? 6:46 a.m. right? You can see 6:45 is what he's saying. Just now it was actually created for us. So you can still see that the original file is going to be there. It's just like it's making a copy of it. Okay, you can do the same thing, guys. In fact, I'll just go back and rename the file. I'll probably copy and paste it here. I'll probably call it as insurance2.csv right now. Okay, so instead of using a put function here, right, you can also say copy from local. There's also another version of the same function. You can say copy from local. This is also another version, very much identical to the put only. There's no changes at all. It's the same guy. He's going to copy it from the local and push it into your HDFS path over here. Okay, so this is something called copying. So you are using copy from local function, or you're using put function to copy the file from the local to your HDFS. But now what we will do is use another command called move. -mv is called as move. Okay, we'll say move the insurance2.csv from this area to this folder. It's moving. It's like it's going to completely delete the file itself from the local right now. Okay, so desktop insurance2.csv, right? We did have the file. What was the problem? Okay, what is the problem here? Or move can work for files, right? Move a file or directory only. It is actually okay. I'll try it for insurance.csv then. What's the problem here? Okay, so I'll just type it again, home slash Cloudera slash desktop slash insurance.csv, move it to data. Let's hit enter. I don't know why it's a problem. Untitled folder slash, I'll say everything from this particular folder needs to be pushed here. Now we'll hit enter. Just give me a second, guys. I'll just go back and rename it. Okay, in desktop there is something called ABCD. Go inside that. I want all the files to be moved into this one. No such file or directory. I don't know what is going wrong here. We'll just try it one last time, guys. If it still fails, we'll just leave it. Okay, so let's push this guy here. Now we'll go back and say HDFS DFS -MV. So it is at home Cloudera. I can just go back and copy it. Properties. Let's go back here. Copy this guy, come down here, paste it, slash. The folder name is ABCD, slash, we'll give star, which means within the folder, I want everything to be moved into slash data. Let's hit enter. I'm not very sure why this is an error. In fact, what is wrong? Everything is good. Move home. Okay, so let me check this, guys. I don't know why it's behaving so weird. Okay, so anyways, so it actually this should work for you guys. You can just try it if possible. So this MV should actually work. I don't know what's really going wrong here. So it's actually making a move from your local system, right? Oh, I'm making one mistake. I'm sorry, guys. Yes, it is actually within the HDFS, this move. Okay, I'm making a mistake. I'm sorry, guys. The move works only within this particular system. I mean, within that particular HDFS only. It's not from local to that one. Yeah, I'm sorry, guys. I'm making a small mistake. No. So the problem is, let me tell you something. HDFS DFS -ls slash, right? So we have the data folder. I understood the problem. I'm sorry, it's my mistake. mkdir, we'll create another folder called data2. So the move is supposed to work within HDFS, okay? From one folder to HDFS to another folder in HDFS. So we'll say from data push insurance.csv file to data of 2. So it is moved within HDFS, guys. I'm sorry, I made this mistake. So now you can go back and check your folder data. So we'll go back and say ls, tell me what's available in data. It won't be available because it would have got moved to data 2 right now. Okay, so I'm sorry, guys, I made a small mistake. So the move will actually move it from one HDFS location to another HDFS location. It's not from local to HDFS. Okay, there's actually another command which will do it, where it'll entirely delete the file itself and will move it. I was thinking it is actually this guy. No. Okay, so the MV, the move will basically move from one HDFS location to another HDFS location. Okay, so the first two things that we saw, the put and copy from local, they are moving from local to HDFS. while this is within HDFS, what are they actually doing? Okay. Similarly, of the same sort, you can go back and say -cp. It means copy. The source is going to be, let's say, data2, and we'll say all the files within this folder to plain data to this particular folder. So it's going to make a copy right now. It's not moving, but it's rather making a copying. So now you can see in the data folder also there will be this data. Similarly, in data2 folder also this data will be available. So it's making a copy of this particular data. So we spoke about ls, where it's actually listing all the files, lsr listing it recursively, mkdir, which is making the directory. Then we have spoken about put, which is putting file from local to HDFS, or copy from local function, which is copying from local to HDFS. A move function, which is actually moving files within HDFS, and then a CP, which is actually copying files within HDFS. In the same fashion, you can also say RM. RM stands for remove, which will remove the files or the folders itself that you are saying. Okay, so actually, I'll tell you. So we are saying remove from this particular folder the insurance.csv file. Now you can go back and check this particular guy would have got removed. So look at the data too, it would have got removed. But if you're removing a folder, please make sure that you say recursively. So it means he has to delete the folder as well as the files on the inside, else it will not work. Okay, you need to say -r. So now you can go back and check if the folder data2 itself is available or not. It will not be there. It would have probably gone off. So what happened? So we said -r data2, right? It should have got removed. This is listing RM. Okay, you can see data2 is gone. So let me tell you all again, guys, the different commands. HDFS, DFS, LS. It's going to list everything. Adding a R is going to do it recursively. This is command number 1. HDFS, DFS, mkdir, telling this is the folder I wanted to create, will make a directory for us. We've spoken about this one. HDFS, DFS, put, you can tell from which location of local to be moved into which location in the HDFS, or you can also say copy from local, right? Similarly, you can say HDFS, DFS, move files in data1 folder to data2 folder. It can move the files from data1 to data2, right? Or let's say data to data2. Similarly, you can also ask him to copy the files from, let's say, the data2 folder to the data folder. So this is a copy command which will do it for us. Now, finally, if you want to remove something, just go back and say, -rm, remove recursively this entire folder itself for me. So you can say data2 folder itself has to be completely removed for us. Okay, so now you can go back and say HDFS DFS -ls/ you can see the data2 folder himself should get deleted completely. Okay, so these are the different HDFS commands we have, guys. Similarly, you also have another command. Okay, it's called disk usage. So you can ask a question, HDFS DFS, can you tell me the disk usage in this particular folder called data? So he's going to tell you how much of data have you used in bytes. So 55,628 bytes is what you have probably used, right? So he's going to tell you how much of space you have probably used in terms of bytes over here. So this is called DU. It's going to basically tell you the disk usage of how much you have probably used right now. Similarly, guys, now suppose in case you have done some computation, okay, and you have a file available in HDFS, you want to move it to local. So you have a file in HDFS, you want to move it to local. put did what? He was putting file from local to HDFS, right? But now what we're going to do is we are going to get file from HDFS to local. So we will go back and say HDFS, DFS, I want you to get this particular file, somebody called insurance.csv, and save it in the local, which is home slash cloudera slash desktop slash, or easiest would be go back and copy this guy. So we are saying from the HDFS, I want you to save it in this particular local desktop here. You see? So we are saying HDFS DFS, I want you to get this file available inside the HDFS to this particular local space is what we are saying. Now the moment you hit enter, you can see he's going to go back and fetch that particular file for us. I don't think probably data is available, or let's check if data 2 is available. DFS ls slash okay, then within data, is it there? Oh, even within that there's another folder called data. Now you can see, okay, so the change is get data slash insurance.csv. This file has to be, pulled from the HDFS, and you need to save it in the desktop right now. So you can go back to the desktop and check whether this file has got saved. He's going to tell us, okay. You can see desktop, where is this guy? Home desktop is what we gave. It's not there in desktop. Should we pull it to ABCD then? We'll ask him to get it to ABCD folder. Now you can see the insurance.csv file is there. Sorry, previously it would have then overwritten it. It would have probably overwritten it. I think that's the case. Okay, so now you can see he is able to get that particular from HDFS to your local system over here. Okay, so what did we do, guys? In the first case we said put basically means you're putting a file inside the HDFS from a particular location, right? So when we go back and say put this one, you can see this is the local location, you're moving into HDFS. But in this last case, you're saying, I want you to get it from HDFS and put it into the local. So that's the opposite of it, right? So this is basically what you're, you're saying, copy it from my HDFS and push it into the local. So that is basically the meaning. Okay. So we have seen a couple of commands, guys, starting off with HDFS DFS ls, which is going to list the files. DU is disk usage. MV is move within HDFS. CP is copy within HDFS. RM is remove a particular directory within the HDFS. Then put, we know, is going to put from local to HDFS. Copy from local will copy the file from local to HDFS. Similarly, move. Now I got it. It's actually called move if I'm not wrong. Move will permanently delete it. So when we say move from local, home, Cloudera, desktop, ABCD, let's say insurance.csv to data, he'll move it permanently. So this is what I wanted to try. You can go back and see. You can see the file is no more. It has moved it actually permanently. There's a difference between copy from local versus moving it from local. So when you say copy from local, it will just make a copy of it. So go back and say copy from local, it will just make a copy for you. It will not delete the file for you. Whereas if you go back and say move from local, then it's gone. That file will be deleted for us. So it's called copy from local versus move from local. So this is what I want to try. The plain -mv is within HDFS. Okay, this is move from local. I thought that one will do it. It's move from local, who will move it permanently from local disk to your HDFS here. Okay. So any other commands? Another command will be cat, C-A-T. Basically, it's going to print things for us. So we can say HDFS DFS, I want you to print in this folder a file called insurance.csv. So it can print that particular file for us. Can you see? So the cat is basically what? It's going to print it for us. He's going to tell us what is the contents of this particular file here. It's called std out. It's basically printing it out for us. So he's saying these are the different contents inside that particular file. So you just have to say -cat and tell him what is a file. He'll be able to print it for us. Okay. So these are the different HDFS commands that you need to understand, guys. So how you can basically read and write files in and out of HDFS, from local or save it to local. I think probably we might have discussed 13, 14 different commands, if I'm not wrong. So these are some of the most important functions that you need to understand here. So I think I was a little fast. I'm sorry for it, but yes. So one last time, HDFS DFS. One is LS. So I'll probably create a quick note. So you're saying HDFS, DFS, -LS, give him the path, he will list it for you, right? Similarly, if you just go back and say LS, but R, it means recursively, all the files within the path, within all subdirectories, etc. HDFS, DFS, RM will remove the files from this particular path, or at least the file. But when you say remove it recursively, everything available within the folders, the subfolder, everything will be removed. Then HDFS, DFS, move from this source of HDFS to this destination of the HDFS. So please understand that is within HDFS only. That is the function called move. Then HDFS, DFS, CP, it's called copy from this particular source to this particular destination. Once again, only within HDFS. Next is HDFS, DFS, which is put function. The source is local source. I'll write it as local source to HDFS destination. Right, this is called put. Then similarly, somebody called as get is there, where get is going to do the opposite, where he'll get it from HDFS and push it into local. And similar to the put that we saw previously, right? There is another version of it. It's called copy from local. Right, he's going to copy it from the local for us. Or otherwise, we can also ask him to move it entirely from the local, which means not even a copy will be kept there. This is called get function. Apart from that, we have spoken about mkdir. So you can tell him, hey, make the directory in this area. This is the directory I want you to create, right? Mkdir. Then we have spoken about HDFS, DFS, DU called disk usage. Tell me how much of disk has been used in this particular folder here. So these are the different commands that you need to understand, guys. I think we have what, 5, 10, 12 or 13 commands here. So these are the different commands that you need to understand about HDFS. Practically, what would you do with this particular guy here? Okay, with HDFS, how would you pull in data? How do you push out data? How do you move data within this guy? Okay, how do you, probably print it? So for printing, cat is there. We missed that. DFS, cat, this particular guy followed by the file name. He can print it also for us. It'll let you know what is the contents on the inside. Okay. So any questions till here, guys? Is it okay following till here? Yeah. So these are all basic Linux commands, right? So only difference is you're saying, hey, this is a separate hard disk reserved for my HDFS, and all the commands I should just write a HDFS DFS at the very front. That's it. So these are the commands which will basically help us manipulate the HDFS over here. So there's nothing to do with yarn, guys. Yarn is something that's not in your control. You can never do anything with that. You just have to understand that he is a process who will do it. Similarly, name node, data node, you don't have any control over it. You can't do anything with these guys. These are all processes. You just have to understand that these daemons. Daemons means never-ending process. There are processes available at the back end. You just have to know the theory behind it. You can't control any of these people. There is no commands to control these people. Okay. And probably there's also another function. I haven't tried this, but I remember reading it. Hmm. So actually you can say replication. Okay, I think he's going to make duplicates of it. We can try it. Okay, so we'll say HDFS DFS set replication, and the replication number, let's say 4, probably for a particular file, which is data/insurance.csv, let's say. Okay, so this is actually a replication factor that you're keeping. Can you see? Replication has been set, which means if you go back and list it, will it show for us? I'm not very sure. It's not showing, but here you can see replication number. The replication number is showing for us. It's 4. So probably this file was replicated somewhere. We don't know. Okay. But you can keep your replication factor also for a particular file. If you feel the replication has to be higher, right? You can set your replication factor also. I haven't really seen it in proper actions and all using many servers, but yes, I remember this one. Set rep followed by what is the factor for replication. So you can say set replication, the factor, then you just have to tell him, the path. And for that particular path, that particular file, he'll be able to keep the replication for us. Okay. This is one last command. Okay, so something called set rep. I don't really think it'll help us probably, like how it might help a Hadoop admin. Okay, so I think with this we have completed HDFS, guys. So we understand how HDFS works. We understand how to make use of HDFS in pulling, pushing files, etc. Yarn also, I hope it should be clear because it's more of just a theory. Now with this, what we can do right now is we can jump into Hive. Okay, another very important component that we spoke about, right? We have something called as Hive. What is a Hive actually going to do? I told you, right? It's more like a query engine. It's a query engine who can help you write SQL kind of codes, create tables, query, the tables, etc., do some analysis. So the next component that we're going to be discussing is something called Hive. So we understand HDFS, we understand Yarn. HBase is a little out of scope. Okay, we'll talk about Hive right now. Okay. So Hive is once again simple, guys. I'm assuming some of you might have worked with SQL. So Hive is very simple. Hive is more of a simple query engine. Okay, you can go back and create tables. You can go back and push data to the tables. You can query the tables. You can write your SQL queries, etc., to do analysis here. So what we're going to do is we're going to open our Hive command line interface by typing Hive and hitting enter. Just say Hive and you hit enter. Okay, he's launching the Hive software for us at the backend. You can see it's trying to launch it. It's launching all the Java processes. Now you can see Hive is ready right now. So now what you can do is you can write all your SQL queries here on this particular Hive. Say for an example, very simplest thing will be, we can say show databases. Hit enter. It will list all the databases available. So there's a database called default. There's something called test. Looks like I've probably created. There's something called test. Then you can say show tables. So the database that he's using, right? Within that, if there are any tables, he's going to show all the tables for us. Similarly, if I remember correctly, to drop a table, you can say drop this particular table. Okay, so drop default.employee. Okay. I don't exactly remember the command, but I'll let you all know tomorrow. Okay, so it's actually a drop only. I'm not very sure how to drop it. So one was show databases, show tables. They let you know what are the databases available and what are the tables available. So these are the different tables that we have created. I think let's just quickly check now how to drop it. Why do we have to keep it open? Drop table in Hive. Okay, it's just drop table and then this one. Sorry. Okay, so we just have to say drop table followed by the table name. This was the command. So now you can see he's dropping this particular thing for us. Go back and ask show tables, you don't see it anymore. Or underscore sequence, he's removing that also. And similarly, I'll just remove the other things so that it doesn't trouble us. Okay, we can remove this guy, we can remove this guy also. Now go back and ask for the tables. Looks like there are no tables available here. Okay, so you have two databases. We're using the default database if I'm not wrong. Right now we saw a lot of tables. We have removed the tables also. Now let us go back and try to create a table, guys. Okay, but before creating a table, why don't we create a file with all the data so that you can go back and read the file and the records inside the file can be pushed inside a table. Okay, so let us say gedit, it's called the editor name is called gedit. I'll create a file name called employee.txt. Hit enter. It's opening a file called employee.txt. You just have to go back and type it. Okay, I'll say employee number 1. I'll use a piping symbol. I'll call him as John. 2, piping symbol. I'll call him as Robert. 3, piping symbol. I'll call this person as Jill. 4, piping symbol. I can call them as Andrew. 5, piping symbol. I'll call it as Tom probably. Okay, so we have created 5 records here, guys. So we are saying, hey, this is all the serial numbers, but these are all the names: John, Robert, Jill, Andrew, Tom. These are all the names. We'll just save it. So if you have saved it, where should this file be? Let's ask ls. You can see that employee.txt file is in the local. It is available where? It is actually available in the local. I think it's okay even if it's in the local. I don't see it to be a problem. It can read from local as well as HDFS. Hive doesn't see it as a problem. I guess it's okay. Okay, we will see. If it doesn't raise an error, it's okay. If it's going to raise an error, we can change it. But 90% I'm sure it's okay. Now what we can do is we can go to Hive. We can say create table. Table name is employee. Okay, so we're saying table name is employee. Open parenthesis. We need to start giving the variables. Okay, one is we had, let's say, the ID of a person. It was integer, comma, hit enter. The second was the name of the person. It was probably a string. Let's close it. Let's hit enter. So you can see create a table called employee where the fields are ID and name. The types are basically integers and strings. Now what I want you all to do is I want you all to understand your Hive to say that it is row format delimited. It's all in row formats, okay? And they're all basically delimited. And the fields are terminated by a piping symbol over here. We're saying create this table called employee, open and close parenthesis. The fields are ID and name. The variable types are integers and strings. We are saying it's row format delimited, where the fields are terminated by colon. And I want you to store this particular, let's say this table, as you can say a text file probably. Okay, I think it's not about the table. I think it's more about the file here. Okay, I think it's about the file, guys. I'm sorry. So it's about the file. It's stored as text file. We'll give a colon, right? It's a semicolon, right? We'll give a semicolon. We'll hit enter. If everything goes right, you can see he'll say it's okay. The time taken to create the table was 0.434. Ask for show tables. You can see the table has got created right now. So create table, this is the name of the table. These are the variables. It is row format delimited because it's all in row wise. The fields are all getting separated by a pipe, and the file is actually stored as text file. Okay, I doubt this, guys. I think it's more about the table only. I'll tell you all in some time. It's more about the table if I'm not wrong. Anyways, now what we can do is we can say load the data. Okay, load the data. You can say in path if it were in your Hadoop distributed file system, else you have to say local in path. Yes. So in path means plain HDFS. Local in path means it's your local system. Okay. Local in path where the file is available in this particular directory. I mean this particular directory and this particular area. So where was it? It was in the desktop, isn't it? You did create in the desktop. So ls. It's not in the desktop. Okay, it's somewhere else. PWD will tell you present working directory, home Cloudera within that employee.txt. Okay, so we'll go back here. We'll say, hey, in this particular path, it's available. Okay, so it's at /home /Cloudera / the file name was what? Employee.txt. So we're saying home /Cloudera /employee.txt. So we're saying load the data. The file is local. It's in path, in this particular path, into table. Which table? The employee table here. It's all plain English, guys. See, Facebook has made it so simple for their analysts to work on it. So you just have to say load the data, local in path. If it were coming from the local directory, then you're saying into the table here. Let's hit enter. If everything goes right, you can see it tried to load the data to the default.employee and starts number of files, total size is 38 something. I don't know what it is. You can say show tables. Is going to show the table employee. You want to see the records on the inside, just like plain SQL. Go back and say select star from employee and close it. That's it. So we are saying select star from employee. We are giving it a semicolon and we are hitting enter. It's showing the 4 records for us right now. Now suppose in case if it were in the HDFS, right, we'll go back and move it. So we'll say HDFS DFS. I want you to put the file in this particular directory. The file name is employee.txt inside this particular folder. So he's going to put from local to HDFS here. Go back and say DFSLF within this particular data just to confirm it has come here. So it has come. Now, if you were to load the data, the only difference is, guys, remove the local keyword. Remove the local keyword and now go back and say, hey, it is /data /employee.txt and hit enter. Now can you see? So the previous case was the local path, but this is a HDFS path. Now you can go back and say select star from employee, hit enter. You can see that he's basically making a duplicate of it because the first time you loaded it from local, the second time you loaded it from HDFS right now. So this is exactly how you create a table, guys, and you are able to push records to this particular table coming from a file, something like this, a text file, something like this, right? And then you're able to query also from this particular file. So the first case we pushed the file from local, the second case we were doing it from HDFS right now. So this is Hive. I mean, we're going to see more examples. It doesn't stop here, don't worry, because Hive is something that you guys might be using, sometimes frequently. So Hive is something that we'll see more and more examples. Don't worry. I'll take you through all certain unstructured cases also. Let's say, how about handling JSON files? How about handling nested JSON files? Even those are certain examples that we'll be discussing, which we'll probably take it up for tomorrow. So for today, just summarizing, we have spoken about HDFS, we have spoken about Yarn, what are the different processes on the inside, how are they handling it? We have spoken about HDFS commands, and now we started off with Hive, where we created tables, pushed data, and we did some couple of queries here. Okay. Any questions till here, guys? Are you all comfortable till here? Followed all this code that we just wrote? Okay. Vidya, did you follow it the second time when I was telling you? So the load data that you did, right? If you say local, it means the path that you're specifying is a local path. That is, it is not HDFS. It is plain, DS, plain, file system, FS. Whereas when you say in path, it means it's a HDFS path. So the first time when we did, right, you would have seen, we would have done a local in path. Somewhere here. Can you see data local in path, which means this path is a local path. Can you see it's not HDFS path? But here we said plain in path. We didn't say it is a local in path because it is a HDFS location. So the first guy was a local location. This is a HDFS location. If it is a HDFS location, just say in path. If it is a local location, you have to say local in path. You're just trying to distinguish the path, whether it is local or HDFS, using the keyword called local over there. If you say local, it's local path. If you don't say local, it's a HDFS path. Did you follow that? Okay. Okay. So any questions till here, guys? Are you all able to follow till here? Are we good till here?
Hey, one question. See, in the you are in local impact, you have that file employee.txt, and in the HDFS also you have that employee.txt. Is it? So that's why you are moving that into employee table.
Sure. We moved it just now. No, can you see? So we said, hey, from my local, I wanted to push it to HDFS. We pushed it first. Then only that command will work. It will not work if the file were not available. We specifically pushed it first, and then we went on to go back and push that file from HDFS to the table. So this will work only if the table were available in HDFS, which doesn't happen by default. You need to push it.
Okay. Okay. Thank you.
Okay. Great. Okay. So Manohar has a question. So we need to deal only with HDFS and Hive for all the data load. HBase is columnar DB storage. In what scenario will we go for this? If I am not wrong, it's a data storage, right? Even from HBase, you can push data into Hive, or I think Hive, in fact, is storing these as HBase tables. I think there is a small connection between Hive and HDFS. I'm not very sure about it, but I can look up for that. I told you, right? So some of the questions I won't be able to answer since I'm not an expert at these areas. But let me look into it. I think the tables themselves will get saved in HBase, if I'm not wrong. One thing I remember is the metadata about all of these guys will be saved in MySQL. Okay. Using password now. So the metadata about all of this Hive things will be saved in MySQL. So I'll try to open up those cases and I'll tell you. So the metadata, what table, what databases you have created, those kind of metadatas are usually saved in MySQL. I'll try to figure out what this error is, and I think I need to tell the password and all. Okay, so I'll try to figure this one out. The other one was HBase and Hive, let me look into it. I'll let you know about that one. There is a connection between them. Okay, great. Okay, so if there's no other questions, I think we can probably call it a day, guys. Okay, cool then. So thank you guys. Thanks for joining. We'll catch up tomorrow where we'll discuss more about Hive Scoop and PySpark. Okay. Thank you guys.